Okay, welcome to class, everybody, and we are going through Chapter 8 topics in this video, where we are going to review all of our Python skills before we start digging in and applying Python for use in data analysis. And so as you come into this course, one of the prereqs, I believe, for this course is the fact that you've taken the Python course. But I know that if you've had it last semester, it's still been a few months since you've probably done any Python with any intent, and for some of you it might even be longer since you've had Python, so the review I think is really helpful. And then, in between, people sometimes learn other languages and things and sometimes forget some of these skills, so that's why we're doing this. But I want to start with something that's kind of a little bit more fundamental, and that is this concept of problem solving. And I'm going to kind of use Notepad++ here as kind of my presentation tool, as primitive as you guys might think that is. But I want to talk about first this whole concept of problem solving and why we talk about it in programming to begin with. And the thing about programming is you're always trying to solve some sort of an issue. You're trying to accomplish something. And before you really can do it effectively, in my mind, you need to kind of make a roadmap for yourself. Now, most of the stuff that you guys maybe did in the Python course were really pretty simplistic, because you only have so much time in a semester, and you're trying to teach people all the basics. Variables, loops, if statements, lists, dictionaries, etc., objects, classes, and you learn a little bit about the concept, you try it out a little bit with code, and then you move on. And what I'm hoping now that you see is now we're going to just start utilizing Python to actually do problem solving for more complex problems. And in that situation, you really have to start thinking about the concept of what it takes to solve a problem. And this is kind of weird. And I'm going to use a little bit of an example that I use in my Java class. In that you're going to see a little bit of overlap, right? With some of the stuff that you learned in Python. But we solve problems in programming usually using a number of different things. But if you are problem solving, the first thing that you usually have to do is, this is silly, but define the problem. I mean, what is it you're actually trying to do, right? And some people have a hard time verbalizing it, and in many cases will just jump right into writing code. And I get it. You know what? I'm kind of the same way. And that, sharing of thoughts when you're going through the problem solving process, especially if you work with a team, is really sometimes very productive, because you might be thinking about a problem a certain kind of way, and then if you can confer with others, they might have some radically different ways to solve the same problem. And in some cases, one of the benefits of working on a team is that you have many minds working to solve the same thing. But you have to define the problem before you can solve it. Once you have kind of a roadmap of how you think you're going to solve it, what also becomes really necessary with complicated problems is to start writing it down somehow, right? And in programming, our usual go-to is to do this thing called pseudocoding, right? Where you write out the steps of how to solve a problem verbally, and when you think back to that Python class, those of you that took it with me, right? I always do a whole unit on problem solving, pseudocoding, and flowcharting. And one of your assignments there is a recipe, like the first pseudocoding thing, right? And people are like, why do you do a recipe? Well, a recipe is a really good example of problem solving and solving a problem through a series of sequential steps. And that is, something that for some people is kind of intuitive, and for others is really a struggle. And the whole reason why we have recipes for cooking is because for many people, it's difficult to remember what ingredients do I put in here? What order do I mix things in? What order do I prepare the ingredients or the sub-ingredients? Or what temperature do I cook it at? How long do I cook it? And so you write it down, because otherwise you don't do it right and it doesn't turn out the way you want it to, right? So that's the why. And a recipe is a really good microcosm of problem solving, especially for sequential approaches. Another approach that people sometimes use is the flowcharting thing. And for some people, it's easier if you can visually show steps and the sequence and the pathway of the steps, especially when we start breaking out of a sequential series of steps. And let's talk about the three major ways to solve programming problems. All right. Does anybody remember this? What are the three ways? One of them I just talked about. All right. Well, I'll offer it up since nobody's talking. Sequential, or step by step, and that the recipe falls into that paradigm. And very often, problems are pretty simplistic that way, right? You know, if you want to bake a loaf of bread, you heat up the oven, you grab your ingredients, you mix them together, you knead the bread, you let it, the yeast rise for a while or whatever, you stick it in the oven, you cook it, you pull it out, you let it cool, slice it, serve it, and you're done, right? But it's all a series of steps. There's no repetition in it, there's no decision making in it. And those, by the way, are the other two processes. So one is called selection, or decision, if you want to think of it that way. And that would be like our if statements or our switch or case statements. So we have to choose a fork in the road and proceed from there. The other thing that we have is the process of repetition, also known as looping in programming. And so sometimes you have situations where you have to perform a task repetitively in order to accomplish it, and looping is the structure that we use. It's been decided for quite a while in the field of logic, by the way, that logical problems can always be solved using one of these three mechanisms. And so I think that that's kind of interesting to remember. And I like to give an example of this really quick too. And I'm not going to have you do an exercise on this in any way, shape, and form. You did enough of that in your Python class. But I recently was teaching my Java class. They were writing a program for rock, paper, scissors. And the chapter that it's attached to is all about selection. But it also fits into the repetition thing as well. And I was kind of talking through this in my class last night, that if you were playing rock, paper, scissors, it's like this childhood game that a lot of us know how to play. And in the class I usually point out the fact that it's kind of interesting with rock, paper, scissors, because if you teach a couple 5-year-olds to play it pretty quickly, and then have a 5-year-old explain it to another 5-year-old, they can do it in a couple of minutes, and you just show them and do it, and then they get the concept and run with it. But then when you take that same set of instructions and you start to convert it to program code, where, hey, this is a whole different story now, it gets a little bit more complicated. And so what you have to start to do in order to program this problem, and this is one of the issues that my students were having, is, well, okay, I get it. I can just jump right into the IDE and write the code, right? And then a lot of people that do that stumble. And here's where they stumble, because they didn't really think out all the scenarios beforehand before writing the code. And so what I did is I go through this process during the class where I talk about, well, when you play rock, paper, scissors with one other person, you have 9 possible outcomes, and you have to actually sit and analyze that in advance, right? So there's 3 possible ways to win, 3 possible ways to lose, and 3 possible ways to tie, given any selection that you make. And your selections are rock, right, your fist, paper, flat hand, or scissors, the little V or whatever. And for every one of those that you choose, there's also 3 possible reciprocal actions from your component. In this case, when we were writing it, the computer was the component. And then based on each one of those selections by your opponent, the result is listed here. And so this in essence becomes kind of like a little truth table or a logic map, if you will, to help go to the next step, which is actually to pseudocode this. But this is an initial part of the problem solving process. And in some cases, you do have to map things out. You might, with some complicated data analytics problems, you might have to kind of make a table or a chart or a list or whatever you have to do to kind of logic through what happens next. And so where we take this, from that scenario is like, figuring out all the win-loss scenarios. Then we switch over to the pseudocoding. And in this case, what we did is we flowcharted it. And this was something I actually did a number of years ago with, and this might be 4 or 5 years old now, this PowerPoint, but it does show this process that I went through with one of my Java classes when we were pseudocoding this problem. And I know this might be a little bit hard to read on your screens, but I'm trying to have the whole thing on the screen at the same time, within a reasonable degree. But there are a couple of the little arrows missing. So there should be an arrow here and here. But initially what happens is you prompt your user to play the game, and then you have them select, from the keyboard 1, 2, or 3 to represent rock, paper, or scissors. We grab that information. We also then allow the computer or your opponent to make a choice, and then we start doing comparisons. And one of the first comparisons they do in this problem solving is we check to see, did you pick the same thing? Did the players pick the same thing? And if they did, it's a tie. Well, and then either you're going to play again or the game's over, right? And most of the time you play the game over. And if I zoom back out here, I do allow here for you to loop back, and then you can ask the question again and play again. But if they happen to not pick the same thing and it's not a tie, then you can start breaking down the problem solving and then looking at what the user, you or whatever human being made, whatever choice they made, and then compare it to the possible outcomes. So if we know it's not a tie, the one thing we know right away is if the first person chooses rock and it's not a tie, then we can automatically eliminate the first choice from the opponent and go right to the second choice and then determine the winner based on that. And if you follow this logic tree, it covers all the possible scenarios and then also allows the user to loop back and play the game again. And this is just an example. Now, if you have a roadmap like this, it gives you a way to write the code, right? So it gives you a way, now that I've figured out the problem and all the possible scenarios and made it as efficient as possible, all those are stipulations, then I can convert it into code. So we took this as our starting point in class and then ended up writing a Java program. Now, this is a little bit different than Python, mind you, and some of you may have not learned Java and may never learn Java, and that's okay. But it's really interesting when you come from a Python background and you already know how to program a little bit, that you can look at a program like this and very quickly figure out what's going on, even if you don't know the language. And I think this is another interesting thing about programming, is once you learn that first language, you get it under your belt, very easy to pick up other languages very quickly. Because you get the concepts, you get what a variable is, you get an if statement, you get an output, you get all those things, and you just apply it. And so what we did in class yesterday is we coded through this and did, basically these series of if-else statements that basically correlate to that solution that we had. And it helps you write the code. And frankly, without that PowerPoint, well, this becomes challenging, right? And to complicate the matter further, there's more than one way to solve the problem, and that's why this is an excellent thing for teaching, and teaching people mostly selection, but also looping. And one of the fun things we did in class last night is we looked at everybody's solution, so like, I showed people how I did it. I showed them how the author did it. And then we started looking at how all the students did it. And there were probably, like, generally speaking, about 6 or 7 different types of solutions that all worked. Now, ultimately, the one that is most efficient, that has the least amount of code, it would probably be considered best. But you know what? Maybe it's not. Maybe in some scenarios there's a reason why you have a little extra code or whatever. But doing this sort of thing when you have a more complicated problem And this is just rock, paper, scissors, not super complicated. But could you imagine if you're writing a whole full-blown application? I mean, think of what it might take to write the code behind Excel, for example. How do you do all the things that Excel does and give all these options? Imagine what the flowchart would look like for that program. Yeah, it would be absolutely crazy. You might have flowcharts that are like miles wide, for example, for complicated things. So what ends up happening in large application development, by the way, is the application is broken into little pieces and components, a whole bunch of separate programs working together to accomplish the bigger goal, each with their own problem solving, each with their own solution. And when even the sub problems are complicated, you're spending a good deal of time doing the planning. And when you write complicated applications, if you're not doing that, I guarantee you're going to have a lot of problems. And you'll learn that as you go. Simple programs, and frankly, most of the stuff we're going to do in this class isn't going to get like super, super complicated. But as we move forward, things will change. And then if you're prepared to do that and you think about this first, it really can save a lot of heartache and time, frankly. Because if you can logic out a problem visually like this before you start writing the code, that code is a snap. I mean, you can use this as a guide. I mean, basically each one of these triangles is an if statement, and it shows you what the branches are. It's all laid out. You just got to write the code, convert it straight to code. All the work's already done. There's no confusion with the logic. What if statements nested inside of another. It's all mapped out right here, right? You don't have to do it in code, see it doesn't work, and then fix it later. But very useful, by the way. And what tool you use to flowchart? I just use PowerPoint there, but in a professional setting, you would use Visio, by the way, to do that. So that's rock, paper, scissors, an example of problem solving and flowcharting. Now, what I'm going to do to kind of demonstrate some of the stuff that we're working on next is I'm actually going to start to write a little bit of code. And I think I'm going to kind of just goof around a little bit. And I think I'm going to use Code Sculptor to do some of this. And I'm hoping that the fonts work out. I don't know if a Zoom alone will help. Depends on how they did their HTML programming here. But is that pretty visible for all of you guys? Pretty good? I'll assume
that's Todd, that's good.
Thank you, Nick. All right. Now, what I'm about to do now is I'm just going to kind of goof around with this environment a little bit, and I'm not looking to do anything particularly fancy, but I am going to blow away all the code that's in the window here right now, and even these comments here at the top. And with some of the things that we talk about, I'm going to see how much we remember as we kind of move along. So my goal here is to try to get through at least the first 3 or 4 chapters of material from your Python course within the next half hour. You guys game for this? Because it's going to go kind of quick. All right, so the first thing I want to start with is the very first command that you learned with Python is what? What's the first command that we learned?
Print.
Yeah, print. And I just love how beautifully simple it is in Python, right? You just say print, you put up a set of parentheses, set of double quotes, and you do your hello, whatever, command. And then Python is so beautifully simple. We don't need any terminating marks. One line of code is considered a statement. And you can just hit run and voila, you have your output on the screen. Python allows us to do a bunch of different weird things as well because it's interpreted. Do you guys know the difference between interpreted and compiled? Does anybody want to verbalize what the difference is?
Well, I guess in the one case, when it's interpreted or whatever, it's kind of like not translated, but it's not really the final form of it's not the code that actually is run. It's like one more step that compiles it.
Okay.
Is that right?
That's not a bad way to think about it, Charles, but here, let me add a little bit. I'm trying to spell this right as I'm thinking about what you're saying. That's kind of a hard thing to do, by the way.
Oh, yeah.
I'm thinking about what you're saying, and it's almost like kind of bleeding into what I'm typing. But the difference between interpreted code and compiled code is this. Compiled code means that we have some sort of a debugging engine that converts our code, first checks it for errors, and if it's correct, converts our code into what we call machine code or byte code, right? So in other words, it takes our instruction set and converts it basically to a set of ones and zeros that the computer can run natively in the operating system. And then if we were to look at that compiled code, it would be gibberish to us, you know. And in fact, I think the one example I gave my class the other night, and I'm going to see if I can find the same example that I did. So just bear with me here. So I have my file window here, and somewhere in here, I probably have an executable file or two that I've downloaded from the internet. So for example, here's the VPN client that we downloaded from the web. And it's got an extension of MSI, but it's basically an executable file. And here's the funny thing. Once a file or code is converted into an executable, we can't pull it up in Notepad++. And here's this really weird thing I'm going to do. I'm taking an executable file and drop it into Notepad++, folks. And you know what? I don't know if you knew this, by the way, but you can do that. You know, and this is what the file looks like. So if I open the file and put it in a text editor, it's full of a bunch of gibberish that I basically can't read, most of which are, you know, binary pieces of information that get converted into instructions that the computer knows how to work, but have no meaning to us. And compiled code has this other advantage is if somebody's trying to steal your program, they can't read this. They don't see the logic that you use to create it. So the original code is obscured from anybody looking at it. And that's really kind of what it is. The other advantage of compiled code as well is that once it gets to an operating system to run, it will run significantly more efficiently than interpreted code. Now the difference, what does interpreted mean? So if I took a Python program and ran it, I can look at the code if I have the Python program completely available to me. So the way that a Python program operates is basically this. So compiled code turns into ones and zeros. And, you know, only the computer can read it. Interpreted code just runs. That's all there is to it. There's an engine in the operating system that takes the instructions and on the fly executes the commands. It is not turned into binary information. There's just an engine inside of your machine, thanks to the Python libraries, that just executes the code and does whatever is listed. And so that's a significant difference. Does anybody know another language that operates the same way? All right. Maybe you don't know the answer to this, but I heard somebody say something.
I said JavaScript.
JavaScript is one of the other more notable ones. And the reason JavaScript is that way is JavaScript is the language of the web, right? So that is, you know, in a browser knows how to run JavaScript. Our operating systems also know how to run JavaScript. And that's also been a really super hot area of development too. So it doesn't require it to be compiled. And of course, on the internet, you can't, right? So like if you're pulling down JavaScript from a web server, the browser needs to know how to run it. It does not need to turn into compiled code. But that's the functional difference between the two. All right, so let's go back over to Code Sculptor if I can figure out where the heck I have it here. Okay, that's not the one. This is the one. And let's move on to kind of the next topic here. So after you learn how to do your print statement, you usually learn how to work variables. Here's another real interesting feature when we compare Python to a compiled language. And I'm going to go back to my rock, paper, scissors example here. And I want you to notice at the top of this Java program, I have a listing here. And what I have is basically a series of variables. And in fact, really the first 5 are variables. And you'll notice that unlike Python, I have to declare my variables and in some cases preset their value. And you notice that this user variable is an integer. And in Java, I have to pre-declare the data type, whether it's numeric or characters, right? So you see integers here, you see strings. If I wanted floating point numbers, I would use a double or a decimal, And the interesting thing about languages like Java is they probably have about 10 different numeric formats with different capabilities and capacities to hold numbers. So like when I'm writing a program, I have to think about these things in advance, what data type they should be, and then plan accordingly, and then typically predefine them in a program. You'll notice we have some special ones here, which are finals. These are how we declare constants in Java, which you can actually do, meaning once I declare this variable, this is a value that cannot change in the program. And in Python, we do that symbolically. We just name something all uppercase, if you guys remember. But if we were writing something in Python, and I just, call something, I'll use my goofy whatever, and I assign it a value, I can put a number in, right? And then just to show you that it's actually doing it, let's do a print statement and then just output the variable. And we'll just kind of alternate here. So if I run this right now, you'll see that whatever is a variable that's holding the value of the number 1. In this situation, 1 is a integer because we typed it in as an integer. Now I'm going to say, hey, whatever, why don't you become a floating point number and make you, just type in a bunch of things after the decimal point, and let's reprint whatever. And in Python, I can do this. It will allow me to change from an integer to a floating point number and just roll with it. By the way, JavaScript allows you to do the same thing, which I think is interesting. And now what if I decide that whatever instead is going to be, now it's going to be a bunch of words. All right, and then I print it out again. Yes, it can dynamically change. The variable can dynamically change from one data type to another on the fly. Now, I wouldn't call this good practice. Like, I wouldn't write a program and intentionally try to do this. I have seen programmers that do it intentionally, though, mostly in JavaScript, and mostly a result of them not knowing what they're doing, but it still works kind of thing. And Python is hyper flexible that way too. So it doesn't care. Oh, you want to put a string in here? Okay. You want to put a floating point number? Okay. It doesn't care. It just does it, and that can be positive or negative. Now, there is this implied approach also that if you take something and you make it all caps, that hypothetically that is a locked in value. And so if I'm to print, whatever again, is that going to print 5.5? Nope, it's not going to, right? It's still going to print whatever because here, there is case sensitivity on those variable names. So I can't just switch it to uppercase. So if I wanted to print that other one, I would print it with its exact variable name. So it is case sensitive in whatever you name. And now you can see that output. But this is kind of a convention, by the way, that people have used so that when you are naming uppercase, things with all uppercase letters, and if there's logical words that go with it, you usually do it with an underscore to separate them. And I'm trying to type stuff here, but here we go. I just can't do it. Whereas if I'm doing a regular variable name, I say whatever, where you can use your camel casing, where the typical thing is you start with a lowercase letter on the first word, but every logical word within the variable name then gets capitalized with the first letter. The tendency also in modern programming is to be very verbose with what you name your variables and your methods and your programs, by the way, to indicate what it's actually for. So if it's a variable that's holding, let's say I'm trying to type property here, property tax rate for Racine County, and that's what, let's say it's, I don't know, $2,350, per thousand or something like that. and that's probably not even close to anything that's right. But by looking at that, I know what's in that variable just because of the way it's named. And I would always encourage you when you're naming your variables to think about it that way. Be verbose. Name it in a way that's meaningful. And if you're not being verbose, then please, add a comment, with it. So for example, and here's the thing that, we probably want to talk about too is commenting techniques. So you can always use the CSS style commenting, by the way, which is / ****. I think it also supports the single apostrophe commenting. I think that comes in as a comment. And I think you can also do the double slash comment. And these are all comments here, right? But if you're not really
symbol.
Thank you. Yes, the pound symbol can be used as well. And am I like mixing languages here? That's possible. Yeah,
I always use the slashes and the slash asterisk in Java and then in C. But.
Yeah, and it seems here that these two are not flagging as comments. So maybe we want to review those. Somebody might want to look it up for me and verify if you could. I have this conundrum where I sometimes teach so many languages during a semester I forget which one I'm teaching. And so that's okay if you admit that you don't remember stuff because, frankly, how are you supposed to remember all this stuff, right? We have the internet and Google. That's the reality of it. All right, so let's move on past some of this stuff. And now let's start to look a little bit at some of the mathematical components. And one of the most important aspects of doing math inside of Python is just simply knowing your operators, right? So all the standard math operators apply. So we have, for example, if I'm adding, here, I'm going to change this variable name. So I have a whatever 1 and a whatever 2. And if I wanted to do some math and store it in a variable called answer, I can just say whatever 1 plus whatever 2. And so I can do my math like this and then simply do a print statement to get the answer. And I'm going to run this. I know this is getting, oh yeah, see, yeah, this doesn't like these. So I'm just going to blow these away. And I'm not sure if this is relative to this tool or the language itself. Let's try running that again. All right, so now it's catching all my typos here. Thank goodness for rapid application development. Okay, so I got a whole bunch of these. So I'll fix it like this. Doesn't really matter. I'm not looking at making a perfect program here. But you guys are catching all the mistakes. So that's the whole thing, is knowing how to read your debugger too. But here's the result. So whatever 1 plus whatever 2 was stored in the answer, and then the output comes here. And you could check the math if you wish to see if it's correct. But in terms of mathematical symbols, we do have, addition, subtraction. Those are pretty easy. Remember, multiplication is the asterisk. Division is the /. Are there any other math operators you guys can think about?
There's a few. Modulus and exponentials with the double asterisk.
Yes, exactly. And so modulus, how do we do modulus? Do you remember the character for that?
It's the ampersand? Or is it percent? I don't remember which one.
Yeah, it's the percent sign is modulus, which is pretty common in most languages. Now, modulus, of course, is what we call remainder division. And, so for example, here, like a real common, one would be to see if a number is even or odd. And in this case, I'm doing a mod of the number 1, which is not going to work out well, because there's going to be a remainder of 1, but that's an indicator that it's an odd number as opposed to an even number. So it's the result of the remainder of the division. So is there a remainder or not? What is that remainder? And that's one that's pretty useful as well. Another concept, and I guess we've already been covering, is this whole concept of strings. So strings are characters that are typically encapsulated in double or single quotes. In my typical pattern, and what I recommend to students, by the way, is that typically, you know, my go-to is using double quotes in most programming languages. And then why do they allow both? So that you can nest single quotes inside of double quotes is the answer. But whatever you're doing, make sure that you always encapsulate. So if I wanted to put single quotes around the word bunch here inside double quotes, this single quote has to end before the opening double quote. So it has to be encapsulated inside of these double quotes to work.
Does it not need to be escaped? Or how does that work?
Yeah, well, see, Anthony, if you're mixing them, so let's say if I wanted to print out double quotes here instead of single quotes, then I would escape. So in other words, I would do this. And then that would allow it. So yeah, those we will talk about those escape characters as well. Single or double quotes typically will work. What about let's move on. I'm trying to get as many chapters covered here as possible, and looking at the clock going, boy, I was very ambitious with my thinking that I would cover all this stuff in one session. But let's move on to the concept of if statements. So if statements are one of the ways that we do the second logical problem solving components, which is making selections in programs. So in a really simple scenario, an if statement will have some sort of statement and then an action that follows. And Python kind of has a special way to do that. Does anybody remember the syntax? So let's say if I wanted to check to see if whatever 2 is greater than 5, how would I write that? Let's see if you guys remember.
Remember how to do it in C, not in Python.
Remember in C, but not in Python?
Yeah, parenthesis, I equals, or no.
You say whatever.
Yeah, no. That was before loop, my bad.
Is, what were we checking for? Greater than 5,
greater
maybe?
Than 5, yeah. That's all it is,
and then
colon, next line.
Say that again, Anthony?
I said colon.
Yeah, colon. That's what I was looking for, to see if you guys remember that part of it. Because this is the unusual part of Python, is it does a lot of stuff with that. And then when you move down to the next line and you indent, what's the indent amount you should use?
4?
Yeah, I'll tell you what the answer is. It depends, right? I think technically Python likes either a 2 or 3 character indent. But whatever the indent is, it has to be consistent. That's really the truth of it, right? So if you're always indenting 2 spaces, you should stay with that. If you're always indenting 4 spaces, stay with that. And that's how Python determines how code is encapsulated. So inside of an if statement. So for example, if I decide to do 3 and then do a print command, what would what should I output here? It is greater than 5. Now this is highlighting red, so it's telling me it's wrong. So what am I doing wrong?
I think that's just the string color.
Okay.
For this, for the website or whatnot.
All right, let's run it and see. Okay, so it does work. So is this just showing us that it's indented, and it's part of the if statement? What if we're doing an if statement and there's an alternate situation? We use the else, right? And now I hit the tab key. That's one of my habits too, in some IDEs.
Yeah. So does that just not exist? Like tabbing and stuff in Spider doesn't like it either. Sometimes I don't know. I might just be not doing something. Never mind.
It's quite all right, Anthony. And if you're doing that and you're playing with this in Spider, more power to you. I'm going to flip the sign here on the if statement so that we can trigger the other condition and run this. All right, so else. So apparently that's not how we do it in Python. What's the else command in Python?
Just missing the colon.
Ah, yeah,
Yeah, that's what I was gonna say, the colon.
very good. All right, so I'm glad you guys are kind of remembering that. Yeah, so Python's a little bit weird that way, and there's no need to put curly brackets or any of that stuff. All right, so that's how we do basic if statements, and then of course we can always nest if statements inside. And so if I wanted to do another level of if, I could do it here. So I could say if whatever one is less than 5, and I forgot my colon again. See what happens? And how many was I indenting here? See, that's the other thing. I was doing 3. Just to try it. And we know the condition is true. Right? Is it? Is whatever one less than 5? Yep.
Yes.
Yeah, but what's happening here is this scenario is not ringing true. So now it's not even hitting this first if, because that condition wasn't true. So this, I just switched the sign to make it true, and now you're going to see the oh wow. So you can nest an if statement, and you can also nest an else, etc. Which we also kind of saw with the rock paper scissors thing. Now, have you guys have a recollection here of Boolean variables? You guys remember what those are? So what's a Boolean variable?
Yes
True
or
false.
no?
Yeah. Yes, no, true, false, 1, 0. But usually when we write code, and so let's say I have a different variable. I'm trying to think of a non-important kind of name to use here. Just call it junk equals true, for example. So you can set a Boolean variable just as simple as that, or the keyword false. Right. Now, the reason we talk about Booleans together with if statements is whenever we have a statement that follows an if, conditional statement where we make a selection, what we're really doing is checking to see if something is true or false. So if the statement is true, we can trigger code to happen. But what if I just change this? So I'm going to take this junk thing here and place it up here, and instead of checking to see if something is greater than something or equal to something, I can also just check to see if it's true or false. And so if I type in here junk, what will happen with this output on this?
It'll just print the other thing.
It will print the other thing because this is false, so this comes in as false, so the first part won't execute. It should just print the other thing. Let's try it. And apparently it doesn't like my thing. So what am I doing wrong?
Capital, maybe?
Yeah, I think that's it. This is another one of those things where, language differences. In Java, it's all lowercase, so I've been spending a lot of time there lately. And right, so then if I switch this to true, of course, I'm assuming a capital T, right? And I run it again, now it's doing the other one, and yes, the second if statement's triggering as well.
Question, do you need the parentheses on the if statement when you do put in a Boolean like that?
Here?
Yeah.
Let's find out.
I would assume so, since it has.
Yeah, it doesn't. Well, you know what? Here, let's change this to false, because I think what's happening is it's running and the output's identical. Right. So,
yeah.
So, yeah. And yeah, you're right. And Anthony, once again, this is one of these things where jumping from language to language, I'm showing you the flexibility of Python. Python's like, oh, you put parens in? Okay. you didn't put them in? Okay. It just does it.
Yeah.
Yeah. And
I
that,
wonder if that one works though.
which one?
The one that you just changed, you just took it off, but it's still like an equation.
Oh yeah, that's a good point. In fact, we should set this to true, right? So that one runs.
It did. Okay.
Yeah, just fine.
Huh.
All right, folks, we are out of time, unfortunately. But when we come back next week, we're going to pick up with talking about looping, and we're going to go through like chapters 4, 5, and 6, super rapid fashion. But what I would strongly implore you guys to do if you get a chance here, and let me just bop back over to the unit, is another good way to brush up on some of these skills if you're not remembering them, is we have one of the LinkedIn Learning courses queued up here. And so I think some of the more important things, hello world, variables, we've kind of covered, I guess, the first couple bullets and the conditional structures a little bit, but these are all pretty short videos. I mean, this is what, like a half hour, 45 minutes worth of video here that you can watch to kind of refresh some of those ideas and concepts. So take the time to do that. Remember, we don't have a book for this class, so this is kind of your book. Watching those videos. Remember, I also have all the videos from the Python course here, and the PowerPoints where you can kind of review stuff. And that would be your critical steps for next week. And if you look at also the assignments here, these are kind of parsed out a little bit. So there's 2 sets of exercises here. And for next week, what I would like you to do is start working on the Python review part 1. And then for the following week, we will work on Python review part 2 and move from there. There's also a quiz here, so don't forget to take the quiz. And then I will be posting this video shortly after we are done here, I hope.
And for both of those homeworks, it's all of the exercises in the doc?
Yes, everything that's listed in the document, correct.
Okay.
All right, folks. I will see you all next week. This video ends here.